So welcome to National 4 Chemistry. This is our first video from Unit 3, and the topic for this video is metals. And there's quite a lot that we need to know about metals. The first thing we need to know about are some of the reactions that metals can do. And different metals will be able to react with different chemicals. And there are three chemicals that we need to understand how different metals can react with. And those three chemicals are water, and water is a really unreactive chemical, so only the most reactive metals will be able to react with it. Secondly, we've got dilute acid. It's a reactive chemical, so other reactive metals will be able to react with it. And finally, we have oxygen. Oxygen is a very reactive chemical, so even unreactive metals might be able to react with oxygen, but they wouldn't be able to react with acid or water. And we can summarize a list of metals which are found in the back of your data booklet, what chemicals the different metals react with. So if you have a data booklet handy, turn to the back and you'll see a list of metals. There will be equations written beside them, but we're just worrying about the names of the metals. Now, the four metals at the top, lithium, potassium, calcium, and sodium, they're the most reactive metals. All the metals at the top are the most reactive. They can react with water, they can react with acid, and they can react with oxygen. Now, the next metals down, magnesium, aluminium, zinc, iron, nickel, tin, and lead, those ones cannot really react with water, but they will react with dilute acid and they will react with oxygen. So those are our second, they're reactive metals, but they're not very reactive metals. Our next group of metals, lead, copper, silver, and mercury, they don't react with water and they don't react with acid, but they can react with oxygen. These are our less reactive or not very reactive metals. And then finally we've got gold at the bottom, and gold doesn't really react with anything, which is why gold, if you have anything made out of gold, gold doesn't tend to tarnish. Gold tends to stay shiny for decades at a time because it's not reacting with anything. We're going to look at these different reactions in a bit more detail next. So firstly, metals reacting with water. Only the most reactive metals can react with water because water itself is not very reactive. Most of the metals that can react with water are found in group 1 of the periodic table, and they're called the alkali metals. Magnesium is in group 2. It's strange in that it can react with water when it's been boiled and turned into steam, but it cannot react with cold water. So if you added magnesium to a beaker of water, nothing would happen. But if you were to hold magnesium over a kettle as it boiled, you would see the silver color change. And when you normally see a metal reacting with water, you should see fizzing, and with some of the very reactive ones, you might even see a flame appear. Next, we have metals reacting with dilute acid. Most metals can react with dilute acid because acid's relatively reactive. The metals that don't react are copper, mercury, silver, and gold. They cannot react with acid. So if you add them to acid, you won't see anything happening. Now, the equation for metals reacting with acid is that it's a metal plus acid forms a salt and hydrogen. Now, this is very similar to the sorts of equations we had in Unit 1 for acids reacting with alkalis, where we had a salt and water. The difference here is because it is a metal, rather than water forming, we're forming hydrogen gas. So because hydrogen is a gas, you will see these reactions bubble if the metal is reacting with the acid. Now we can test and prove that those bubbles are hydrogen gas by collecting the gas and then setting the gas on fire. Now hydrogen burns with something that we call a squeaky pop. It's a very characteristic sound and it sounds a bit like this. That's the sort of sound you're looking for hydrogen when you set it on fire. That's proof that it's hydrogen because other gases don't make that noise. The final one is metals reacting with oxygen. Now, every metal other than gold reacts with oxygen, and you can tell that a metal has reacted with oxygen because you see a color change happening. For example, magnesium will turn white. Copper will turn from a nice pinky brown shiny copper color to black. Iron will go from silver to grey, and other metals will turn white or grey and they'll no longer be shiny. What you're forming when you react a metal with oxygen is a metal oxide. The most reactive metals need to be kept away from the air because the air contains oxygen, and so they get stored under oil to prevent a reaction from happening. So just to summarize that again, only the most reactive metals found at the top of this table can react with water. If you can react with water, you can also react with acid and oxygen. The metals in the middle of this table can react with acid and oxygen, and the metals at the bottom can only react with oxygen. And our solitary element right at the bottom, gold, does not react with any of those chemicals. Our next topic is how do we extract metals? How do we end up with pure metals? So some metals, like silver and gold, you can find them in nature. You might have seen people like on TV programs going to rivers or digging up gold. And you can sometimes also do that with silver. But most metals are actually found inside rocks. And they're found as compounds. And a rock that contains a lot of metal is known as an ore. And metals need to be extracted from their ore. And there are three methods. You can use heat on its own, you can use heat and carbon, or you can use electricity to extract the metal. And if you use electricity, that process is called electrolysis. Now, this list of metals should be familiar. And on this, we can see how to extract different metals. Now, gold, as we said, it exists on its own, so we do not need to extract it. The next metals, mercury, silver, and sometimes copper, they can easily be extracted just by heating up the ore. If you heat up silver or mercury ore, you'll actually see the liquid metal start to rise up out of the ore, and it's quite an interesting thing to witness. The next metals, zinc, iron, nickel, tin, lead, and this can also be done for copper. You have to heat the ore up, but you need to mix it with carbon as well. Now, carbon's a black powder. What that carbon does is it actually helps remove any oxygen that's been reacted with the metal in the ore to form carbon dioxide and leave the metal. So those ones in the middle, you need to heat them, but you also need carbon. And then, quite nicely at the top, all of the metals at the top end in the letters I, U, M. And in order for you to extract those metals, you need to use electrolysis. Now what this means is that you melt the rocks, so you do have to heat them up. You melt the rocks and then you attach an electric current to your liquid rocks, and the metal will remove itself from everything else and move towards one of the wires that you've got going into your container. And so you can get all the pure metal forming on one wire and everything else will move towards the other wire. And that's what electrolysis is. So here's a diagram showing electrolysis. We've got two wires with two rods going into a solution. And we can see that on one rod, copper metal is going to, and everything else is going to the other electrode. For electrolysis to work, we need a DC power supply. That just means that the electricity is flowing in one direction, and because it's flowing in one direction, it means that the metal will move to just one of your two ends. And the electrodes need to be made out of graphite, because graphite itself is not a metal, so it won't affect extracting the metal, and it can also conduct electricity. Our next topic is corrosion and rusting. Now we've seen that some metals can react with water and oxygen, and these metals, if you leave them out in the environment, in the atmosphere, they will slowly react with water and oxygen. Now that reaction is called corrosion, and we can see corrosion happen everywhere. A really good example is the Statue of Liberty. The Statue of Liberty was made out of copper. So when it was first put up in New York, it was copper coloured, and it has slowly over time turned green because of corrosion. Now when iron corrodes, we call it rusting, and we know that iron, when it rusts, it goes from a nice silvery grey colour to an orangey brown colour, and it also becomes a lot weaker. Now we can actually detect whether or not iron is about to rust using an indicator called ferroxyl indicator. Now this diagram shows a nail that's been wrapped with another metal in the middle. The ferroxyl indicator is actually everything else in that circle. And that nail, the bit in the middle, has turned pink, which means that no rusting is happening in the middle of that nail. But at the two ends, we see that blue-green colour forming. That's showing that rusting or corrosion is happening. And if we look really closely, we can actually see that the nail has already rusted. It's formed that orangey colour. Whereas if we look really, really, really closely, not at the golden spiral in the middle, but between the bits that are spiraled round, we can see that that nail is still silver in the middle. So it hasn't rusted, but the end parts have rusted, and it's turned that ferroxyl indicator a blue or a blue-green colour. Now there are ways in which we can prevent rusting from happening. Because we don't want iron to rust. We don't want it to get brittle, change colour. We want it to last as long as possible. And there are several ways to do that. So the first thing you can do is paint it. And that paint provides a physical barrier stopping water and air getting to the iron. We could also coat it with oil or grease, and that again stops water and air getting in. Then there are some fancier methods. So we could do something called electroplating or chrome plating, and this is where we put a layer of another metal on top of the iron that you have to wait for that metal to corrode before the iron will actually corrode. And a specific example of this is galvanizing. And if we galvanize, what that means is that we coat the iron with zinc. We could also coat the metal, the iron, with plastic. This is what's done for your iPhone charger cables. If you just take the plastic away, it's copper, and if we left that out without the plastic, not only could you potentially get electrocuted, but the copper wires would slowly turn green and they would no longer be able to work properly. And finally, there's something called sacrificial protection, which is explained on the next slide. So on this list of metals, any metal above iron is more reactive than iron. And so if those metals are wrapped around iron or placed near iron, the corrosion will happen to the other metal rather than the iron. So they are sacrificing themselves to keep the iron not rusted. And that's what we call sacrificial protection. So looking at the image we had here, we see in the middle of the nail, that coil, the bit that looks a bit gold, is a metal that has been wrapped around the iron as a sacrificial protection. Now it has corroded and it's what's made it turn that orangey colour, but we can see that the iron that's been wrapped with that has stayed silver and it's been protected. So this is sacrificial protection, where one other metal is used, allowed to corrode instead of getting the iron to rust. Our next topic is looking at how batteries or chemical cells form. So a chemical cell is a way of generating energy by using different metals. So the bit of equipment, the diagram on the right, shows you an electrochemical cell or a chemical cell. What you need are two different metals. The metals need to be different. They're connected with a voltmeter so that we can measure if any energy, if any voltage is being generated. And the metals need to be in a solution that contains ions. And what we call a solution that contains ions is an electrolyte. So any drink or anything that you hear an advert for or read the label and it says it has electrolytes, it just means it contains ions, which is actually most drinks naturally are electrolytes. So it's not a special thing. Now, as long as the two metals are different and they are in an electrolyte, you will produce a voltage. And if you put lots of these cells together, that's what creates a battery. Now, obviously, this diagram shows that chemical cell being quite big, but we can make the chemical cells very small, which is what allows us to have batteries that are also really small, that contain lots of cells. Now, there are ways in which you can change how much voltage is produced. And the size of the voltage is based upon which metals are used and how far apart they are on this table. So the rule is the further apart the metals are, the bigger the voltage. So for example, silver and magnesium are quite far apart from one another in that table. So they would create a big voltage. Whereas silver and copper that are beside one another on that table, there's not a big difference. So they would create a low voltage. Now the final topic we've got are alloys. And alloys are made from metals. So alloys are when we have two or more metals bonded together to make a new type of metal. And the alloy will have different properties depending on the metals that it's made out of. And these different properties will mean that alloys are good for different functions, for different jobs. So alloys that are really light or low density are good for making aircraft. So metals like titanium and aluminium are combined with iron to make lightweight steel that is used in the manufacture of aeroplanes. Alloys that have a high heat conductivity would be really good for making saucepans because they would heat up really quickly. And alloys that have a high electrical conductivity would be good for making wires because they could easily pass the electricity through it. So depending on what properties the alloys have, those alloys are suited to particular jobs. So I know this has been a long video, but that's covered half of Unit 3, which is about metals, their reactions and different properties about metals.